All right, class, today we're going to go over 14.3, which is one-sided limits and continuity. So before we get into continuity, we're going to look at one-sided limits. So one-sided limit is talking about what is the limit from either the left side or from the right side. So far, all of the limits that we've looked at are the limits, excuse me, of both sides combined, right? So now we're just going to be looking at one side. So when we're talking about left-handed limits, we donate them with a little negative sign here. And then when we are talking about right-sided limits, we use the positive sign. So we use the negative sign for left and the positive sign for the right side. The left hand and the right-handed limits help us determine if the limit exists. So remember we talked about that if we had a left-handed limit here and a right-handed limit, as long as they point to the same thing, the left equals the right, then they're equal. We know what the limit is. Where here, the left limit and the right limit are not pointing to the same thing, so we say does not exist. So in our first example here, there we go. So in our first example here, it wants us to find the limits giving this picture. So in the first example here, it's as x is approaching 2, and then there's the little negative sign, right? So that's saying the left-handed limit. So we're going to go to positive 2. So here's positive 2, but we're going to look on the left side of positive 2. So as I get closer and closer to positive 2 on the left-hand side, we're pointing to a y value of positive 1. Whereas B here has a positive sign, so that's the right-handed limit. So as we're approaching positive 2 from the right-hand side, we're pointing to a value of 0. And then the limit as x is approaching 2, well, because the left side is 1 and the right side is 0, those aren't the same, so we say does not exist. Okay. So let's look at some more examples. So if we were looking at number 2, part A, it's saying the limit as x is approaching negative 2 from the left-hand side. So if we look at negative 2 here, as we look from the left, it's pointing at positive 4. As we're looking to the right of negative 2, it's negative 4. So the limit at negative 2, there's no negative, there's no positive, it's just the limit as x is approaching negative 2 does not exist. Okay, now if we're looking at 1 now, so if we look at positive 1 here, from the left-hand side, it's pointing at, probably looks like it's going by 4, so positive 2. As we look at 1 from the right-hand side, it's at negative 8. Then if we look at positive 2, well, from the left is 0, from the right is 0. So because both of them are 0, our answer is 0, right? So look at C and F are very similar, right? Because they're not left-handed and right-handed limits. They're just the limit, and they have to be the same number from both sides. So in C, it does not exist because from the left and right of negative 2, they're different numbers. Whereas with F, because they point to the same from the left and right, the answer is 0. Now, if we look at G, G is as x is approaching negative 3. So if we look at negative 3, I'm going to clear this for a minute because our picture is getting a little messy. If we look at negative 3, and we're looking at it from the right-hand side, so as we're getting closer and closer to negative 3, this is going down, right? There's an arrow going down. There's this asymptote here, and the arrow is going down. So as it's getting closer and closer to -3 from the right-hand side, it's approaching negative infinity. Whereas the limit, as x is approaching -3 from the left, as we get closer and closer to -3, this is going up and up and up forever. So that answer would be positive infinity. So let's look at some one-sided limits, but in terms of an equation and not a graph. So we're looking at number 3. It says, find the limit as x is approaching -3 from the left-hand side. And the function we're looking at here is 6x plus 7. So if you think about it, 6x plus 7 is a polynomial, right? It's technically a line. It's got a y-intercept of 7, and then it goes up 6, up 6, right 1, right, rise over run. And it looks like this. If we look at that graph, right, it is not discontinuous. It's not going to look something like this where it's jumping all around, right? It's just a straight line. So when we want to find this limit, honestly, having it be to the negative or to the positive or no negative or positive, our answer is all going to be the same. So when we want to find our limits, we plug it in. 6 times -3 plus 7. 6 times -3 is -18. Plus 7 gives us -11. Number 4, right, we're going to do the same type of thing. Now, once again, because it's not a piecewise function, we're just going to plug in 9, and it's going to be the same from the left and the right because it's not a piecewise function where everything is jumping around. So if I plugged in 9 here, right, I would have 9 minus 9, which gives us 0 on the bottom, and we don't want that. So remember, when that happens, we want to factor. So we've got x minus 9, x plus 9 on the top, and then x minus 9 on the bottom. Those cancel. Now we can plug in our positive 9. 9 plus 9 gives us an answer of 18. Number 5 says the limit of 3 pi, so we're going to plug it in. Sine of 3 pi. Well, if we think back to our unit circle, 0, pi, 2 pi, 3 pi. So 3 pi is right here. So our y value, right, remember sine is our y value. The y value here is 0. Now number 6 gets a little bit more complicated, and by complicated, it's not really that bad, I promise, because this is a piecewise function. So technically speaking, this graph looks more like something like this, where it's jumping around, right? You might have a dot, you've got this little graph, then it stops, then you have this graph. So when doing something like that, you really have to pay attention to the symbol. So in this problem, it is as x is approaching 3 from the left, right? So if we think about a number line, if we're thinking about the number 3 and we want to do numbers to the left of 3, that would be numbers like this, right? So to the left of 3 would be less than 3. So if we look at our situation here, where it's less than 3 is at 2x minus 1. So we're going to plug our 3 into 2x minus 1 because we're looking at the left-hand side. So we have 2 times 3 gives us 6, minus 1 gives us 5. Okay, so let's just pretend. So that answer is 5. But let's pretend this would have said the limit as x is approaching 3 from the right-hand side. If we made that a positive. Well, if we're thinking about numbers to the right of 3, that would be numbers greater than 3, right? So we would pick this one. We would say, well, to the numbers greater than 3, 3 minus 2 gives us 1. Okay, so because this was originally a negative, we had to plug it in here. If we changed it to a positive, we would look here. So now continuous functions. A continuous function is a function that you can graph without lifting your pencil. So based on the pictures below, we're going to look, is it continuous or not? Well, in A here, right, we have this line, it's filled in there, it keeps going, so this would be a continuous function. This would not be a continuous function because we would get to this hole, have to lift our pencil, put our pencil back down, and continue on, lift our pencil, make this stop. So this is not continuous. We would go along, lift our pencil, put our pencil back down, so not continuous. So anytime that we have a hole here, not continuous, we have a hole, not continuous, right? We got to lift our pencil, come down here, we got a hole, not continuous. So without having a picture, we need some kind of rules. So when we're talking about continuous functions, here are our 3 rules. What needs to happen is f of x needs to be defined at c. What we mean by defined at c is that it's not a hole, right? If you plug 3 into the problem, you get an answer of blank, right? Compared to, for example, I'm going to come back up here actually. In this problem, where was it actually? This one. If I were to plug 9 into the function, there's a hole at 9, right? We got 9 minus 9, which is 0. So that would be not defined at C, right? Or not defined at 9 because there's a hole. Okay, so that's the first thing. It has to be defined. There can't be a hole. Then we need the limit as x is approaching the negative, so from the left-hand side, to equal whatever number this is. Okay, so we need the whatever, when we plug in c, we need that number to be the same as the left-handed side. Then we need it to be the same as the right-handed side. So in other words, we need the limit to equal f of c. Okay, so for example, in number 7, we're looking at x equals 2. Well, at x equals 2 here, right, if we look at x equals 2, there's a hole. So this would not be continuous. And on Math Excel and on your homework, it's going to ask why. So our reasoning would be because it's not defined at C, which you could say in this particular case, C is 2. Okay, so we would say no, because it's not defined at 2. There's a hole. It's not defined. In order for it to be defined, it needs to be a dot. Okay, now let's look at 0. So if we look at 0 here, well, at 0, at x equals 0, we have a dot, so that's good. So it's defined. The left-handed side is pointing to the dot. That's good. The right-handed side is pointing at the dot. So because there's a dot, the left arrow and the right arrow are all pointing to the dot, then we would say yes. Okay, let's look at another one. So in the next example, we're looking at x equals 1. Let me try changing the color here. So if we look at positive 1, at positive 1, it is defined. If you look right here at positive 1, we have a dot, right, at positive 6. So f of 1 is positive 6. However, if we look at 1, the limit from the left-hand side, so the limit as x approaches 1 from the left, that's pointing to the number 2. And the limit as x is approaching 1 from the right is negative 8. So are 6, 2, and negative 8 all the same number? Well, no, they're not the same number, so this is not continuous because f of 1 does not equal the limit as x approaches 1. Okay, so because 6 is not the same as 2, which is not the same as negative 8, then we say it is not continuous. Okay, so when we don't have a graph to look at, if we want to know if the function is continuous at the given variable, well, if we think about what an x cubed function looks like, that's a polynomial. So x cubed looks like something like this. So if you guys were thinking about this problem, is this going to have any holes? No. Is this going to have any jumps? No. So this is continuous, right? It's continuous. I could make this 1,573,000 and my answer's still going to be yes, because there is no point on this curve that there's a hole and it's not jumping around. So we're good. And number 11, this is a rational function. So there could be a hole with a rational function. So in order to double check, we're going to plug in our C value and make sure that we don't get an error. So -7 squared plus 9 over -7 minus 3. So -7 squared is 49, 49 plus 9, 58 over -10. Those are both even, so they could simplify. So I don't have my calculator on me, guys, so pardon my mental math here. 29, this. Now, if I was going to reverse this and I said, where would it not be defined? Well, in order for this to have been not continuous, do you guys agree that if I would have made this number here a 3 instead, well, we would have had 3 minus 3, which would give us 0, and then we would have had to say not continuous. But because that didn't happen, right, that's not what we're doing here, we say yes, it is continuous. Okay, if we look at 12, 1 squared minus 1 over 1 minus 1, well, we get 0 over 0, so that is not continuous. Same thing with 13, 0 squared plus 8 times 0, all over 0 squared minus 8 times 0. Once again, 0 over 0, so our answer is not continuous. Okay, number 14 is going to get a little bit more creative. I'll use creative instead of complicated. So because this is a piecewise function, we have a little bit more work to do. We have to do 3 things. So we have to do the limit, f of 0, and we'll want to find the limit as x is approaching 0. And we want to make sure those are the same numbers. So f of 0, well, where x equals 0, our answer is 2. So f of 0 is 2. Now we need to do the limit. So in order to do the limit, we're going to look at this guy here. So if we were to put 0 in there, we would get undefined, so we have to factor. So we can pull out an x on the top, which leaves us with x squared plus 2. And then on the bottom, we can also pull out an x, which gives us x minus 2. So those x's can cancel. Now when we plug in 0, we have 0 plus 2, which is 2, over 0 minus 2, which is -2, which simplifies to -1. So now we have to look. In order for this to be continuous, these two numbers need to be the same. Well, 2 is not the same as -1, so we would say not continuous, right? Those are not equal, so we would say not continuous. All right, we're almost done. 15, find C so that the function is discontinuous. Well, once again, this is a continuous function, 3x plus 2. That's just a line. It's a polynomial going on and on and on and on forever. So there is no C that would make this discontinuous. Whereas number 16, there are holes for 16, right? So let's factor. So don't you guys agree that if I plugged in a positive 9 here, that would make this 0? That would be a problem. And if we plugged in -9, that would make it 0. So if we had a C of 9 or -9, then the function would be discontinuous. Now, I know that this can be really confusing for a lot of people. This is kind of a hard section. It's a lot to kind of conceptualize and visualize. So if you're struggling, please, please, please join in on one of our Zoom sessions. Email me during my office hours and we can set up a Zoom session as well.